have an assignment that is posted up on Google Classroom that you need to complete by Friday. Also Wednesday, when we have our class, you will again be expected to upload online notes. So before we go forward, let's just quickly review what we've been talking about. So again, this is not the easiest thing to write with. I'm sure I like this. But this is, we're talking about intermolecular forces. These are forces that occur, between or among molecules. These can be contrasted, right, to the concept of intramolecular forces. These are things that hold molecules together. For example, things like ionic or covalent bonding. But how do we get a lot of molecules all together? Well, then we're going to need to use intermolecular forces to hold things together. What gives gases, solids, and liquids their properties that we were talking about? Those are those intermolecular forces. Okay, so just a quick review for IMF, or our intermolecular forces. There are 4 kinds. The first kind every molecule has, and these are what are called London dispersion forces that all molecules have. All molecules have this. So at the very least, for any kind of answer that you can provide with what kind of intermolecular force does it have, a suitable answer is always it has dispersion forces. And remember, these are instantaneous dipoles caused by the fluctuation of electron density. So our electrons, right, we've got our atom, we've got our probability cloud outside of the nucleus, and we've got electrons that are just zipping around. We've got different areas where we know they can be. But sometimes what will happen, right, is the probability cloud will clump in one area. So we have more electrons found on one side of kind of the nucleus rather than the other, and that will create a small instantaneous dipole, which then can induce dipoles in neighboring atoms and molecules as well. So that's London dispersion forces. Second, we have dipole forces. These are contrasted to London dispersion forces in that these are permanent dipoles. And last week during our online class, we did a bit of review about what makes a polar molecule, because these are the result, they result from polar molecules. So all molecules have a dispersion force just because of the random movement of electrons around the nucleus. But ones that are molecules that are polar molecules, they can have this dipole-dipole force. Okay? The third one that we talked about, if any of this is a quick review. If you don't know, please go back and look at the lecture video or the lecture notes from last week. The third one is, it's called hydrogen bonding. And hydrogen bonding is really, it's a special dipole-dipole case. So if you have something that shows hydrogen bonding, it is of course also going to show dipole-dipole bonding, and it's also going to show dispersion forces, because every molecule shows London dispersion forces. So by definition, hydrogen bonding is something that's going to occur between a hydrogen and a fluorine, or a hydrogen and an oxygen, or a hydrogen and a nitrogen. Those are the three cases where hydrogen bonding can occur. And this is what gives a lot of the properties to the biochemistry that makes you up. We talked about last time. So something like water, and I was a little tripped up about it last week about what to call it exactly, is yes, it's the prime example of how water bonds together is through hydrogen bonding. And hydrogen bonding gives water all of its specific unique traits, you know, that it's less dense in its solid form than in its liquid form, because actually the molecules are closer together when they're in a liquid form, kind of sliding past each other. But when they freeze, they can kind of maximize their distance through the hydrogen bonding, creating more space between and among atoms, so increasing the actual volume, right? The mass stays the same, but the volume increases, which also has the effect of decreasing the density of solid ice. And then the fourth case is ion dipole forces. Okay, so this will be the result, say, if we put sodium chloride, NaCl, in water, right? What happens, right, is that the sodium chloride in solution breaks apart to a sodium cation and a chlorine anion, and then this kind of the oxygen of the water gets attracted here. Chlorines get attracted because this is positive, this is negative, and this is how we can bond together. Okay, so there's these four different cases. Okay, what we're going to do today is we're going to look at a few specific kind of questions that you will be asked to do for your homework. So I'm not giving you too much, it's in the homework assignment, but we're going to do a few that are somewhat similar just so that you have a basis to answer some of these questions. So if you have your textbook with you, you can follow along. These are questions on page 440. And we're going to start with number 63. And it says we're given four different molecules. Well, actually, one is an atom. And we're asked to say, what is the IM force? What's the intermolecular force that's present in each molecule? Okay, so for example, so A, we've got Kr. Okay, we should know what that is. A hint, it's where Superman is from. Again, if you don't know your periodic table yet, and we're not saying that you need to have it memorized, or you don't know your polyatomic atoms, again, this is a good chance you really need to memorize these things. Okay, Kr is krypton. Okay, and it's just krypton by itself, so it's not bonded to anything else. So in that way, it can have hydrogen bonding. It doesn't have ion dipole forces or dipole-dipole forces. So the only kind of IM forces that can bind a lot of krypton together, and krypton is one of our noble gases, so usually it's in the form of a gas. The only force that's available here is a dispersion force, because it's the only one. Remember, all molecules at least have a dispersion force, sometimes known as a London dispersion force too. Okay, B, we've got diatomic nitrogen gas. Okay, do we have a dispersion force? Well, all molecules at least have a dispersion force, because all molecules have these clouds of atoms that move around them, and they can temporarily clump sometimes on one side of the molecule or the other, creating an instantaneous dipole. So let's see, so it has a dispersion force. Does it have a dipole? Well, no, there can be no polar bonding because the electronegativity between these two nitrogens is going to be the same. There's no hydrogen that's involved, so it can't have hydrogen bonding, and there are no ions here. So the only one it has is a dispersion force. CO, which we should know is carbon and one oxygen, so carbon monoxide. Okay? All molecules at least have a dispersion force. Okay? There is enough of a difference there in electronegativity. Between oxygen is highly electronegative, so there's going to be a dipole force. There's no hydrogen involved there, so it can't be hydrogen bonding, and there are no ions that are going to be involved there, so it can't be an ion force. You need a metal and a non-metal for that. Okay, the last one there, we've got DHF, which you should know what that is. It's hydrofluoric acid. Okay, so all molecules have a dispersion force. They all have dispersion. Then there's a huge electronegativity difference there, fluorine being one of the most electronegative, so that is going to have a dipole force as well. And then because it's a hydrogen bonded to a fluorine, it's also going to have hydrogen bonding, but we don't have any kind of metal or non-metal there. Okay? So that is number 63. So 64, you need to go through those four molecules and suggest what's there as well. Okay? 65, we can look at it. And again, this is another question of what kind of intermolecular force is present. I think you're going to do 66. But we have, what do we have here? NCl3. So we got two non-metals here. So this is a covalent bond. This is a molecular compound. So this is nitrogen trichloride is how you would say that. Now our question was kind enough to tell us what the shape is. So this is trigonal pyramidal. Okay, which you should know what that is besides the case, because you know that that nitrogen is always going to have that lone pair on the top. It's going to have the lone pair on the top, and then it's going to come down with 3 chlorines like that, the geometry. It's going to make this kind of pyramid shape. Okay, because it's got that lone pair, we've got the potential here for a polar bond. Okay, so what kind of forces does it have? Well, all molecules have dispersion forces. It has dipole, because it's a polar molecule. These are polar bonds, and the geometry of it makes it polar as well. Okay, next one, B, we've got NH3, which we should know what that is. That's ammonia. Okay, we've got nitrogen again. This is going to be another trigonal pyramidal shape. You have that lone pair of electrons on the top, and then it's going to come down like this, again making that pyramid shape. So what do we have here? Well, all molecules have a dispersion force. All have a dispersion force. We've got, oh, what am I doing? I'm drawing chlorine. So these should be hydrogens. Because we've got nitrogen, hydrogen there, then we have hydrogen H bonding, and hydrogen bonding is just a special type of dipole dipole force. Okie dokie. That's B. C, which is silicon tetrahydride. It's telling us that this is a it's a tetrahedral shape. So we've got silicon and then we've got a hydrogen. Like this. And then, let's see. So with the tetrahedral shape, that we've got some symmetrical geometry, so we can't have dipole-dipole. So we can have dispersion forces here, because all molecules have dispersion forces. So no dipole-dipole. If we can't have dipole-dipole, then we can't have hydrogen bonding, and this is the case here. Okay, and then very similar, the last one here, which is carbon tetrachloride. This is going to be the same thing. It's now remember, these have polar bonds. The bonds in carbon tetrachloride are all polar bonds, but the geometry of the molecule cancels out the dipole moments, creating a net zero dipole. So this can't be a polar molecule. So again, all we have here are dispersion forces. Okie dokie. Okay. So next one, I'm going to do these classic questions about, you should be able to tell which one. So question number 70 says, which noble gas has the highest boiling point, and why? So you can't just say guess which one it is, you have to say why. So we need to use our English to be able to tell why. So if we're trying to determine which ones have the highest boiling point, there's two things we need to consider when we're doing this. Number one, we should always consider, we need to consider the type of intermolecular force. Okay, so ones that have ion dipole are going to have the strongest intermolecular forces. So if, say, molecular weight is the same, then the one that has the ion dipole force will take more energy to pull it apart, so it'd be more energy to boil it, to vaporize it, to break those bonds that link it together. So it will have a higher boiling point than, say, one with hydrogen bonding versus one with dipole-dipole versus the weakest one with just dispersion forces. Okay, so that's the first thing to consider, is what type of IMF. And then the second thing that we should consider is, what is the molecular mass? Because as the molecular mass, molecular mass increases, so does boiling point. Okay? Why? Because it's going to take more and more energy to take apart those bonds with increasing molar mass. So let's look at what we have. So we have three noble gases. So we have, what do we have? So we've got Kr, krypton, and we got B for xenon, and then we've got C for radon. So the first thing we need to consider here is, what are the intermolecular forces at play? Well, the only kind of intermolecular forces that these noble gases can have here are the ones that all molecules have. So the ones that all molecules have are dispersion forces. So already you should be thinking, I really don't expect the boiling point for this to be that high. Okay, because dispersion forces are very weak. These are very weak bonds that will hold these together. And when you think about that, that makes sense because these are gases, right? Gases, usually we consider them really not to have kind of any intermolecular forces that kind of hold them together. In some sense, for all of these things to exist as a liquid, to be able to boil them in the first place, they need to be incredibly cold, like minus 100 degrees Celsius, if you want these things to exist as a liquid. Because naturally at room temperature, these things exist as gases. Again, they're called noble gases. So already we expect these things to have a very low boiling point, but we want to know which one has the highest one comparatively. Okay? So since they all have dispersion forces, the only way we can tell them apart will be which one then has the highest molecular mass is what we're going to go for. And the one with the larger molecular mass should have the higher boiling point. So the one with the highest molecular mass there is radon, Rn. So this should be our answer just based on molecular mass. And I looked some of these up for us. So Rn compared to everything else has a molecular mass of 222 grams per mole. It's quite big. And as a result, it's still small, but it will boil, meaning that less than 61.85 degrees Celsius, less than this temperature, it exists as a liquid. Higher than this, it's going to start boiling off into a gas, right? So when we think about it, carbon dioxide is normally a gas, but you watch any of those old movies with test tubes bubbling and stuff in the lab. So what are they using there? Dry ice, or fog machines at a concert. That's dry ice. So that's carbon dioxide that they've gotten so cold that they've turned it into a solid. But just for it being out in room temperature, it's warm enough to kind of sublimate that, to turn that from a solid directly to a gas. Okay, there was one more question I wanted us to look at. The question will be 75 in our book, if you have your book. And then, so 75 says, are CH3, CH2, 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 CH3, and H2O miscible? Okay, so your first question there should be, what does miscible mean? Well, miscible just means, can they mix? Can you mix the two of them together and one will dissolve into the other one? Okay, so I take some water and I take some salt and I can mix it together and the salt's going to dissolve into the water. Okay, and if I looked at it, I wouldn't know it was salt water. I would have to actually drink it before I knew. Likewise, I can take some sugar, put it into some water, it will dissolve. Okay, that means that they're miscible together. But you've known since kindergarten, if you take some cooking oil and some water, you cannot get them to mix together. Those two are immiscible. Doesn't matter how much you shake it or how much you stir it or the temperature changes that it goes through, they are immiscible. So what we're doing is we're asking, are these two things miscible? So we're going to look at this. Probably it's going to be our last unit. I had hoped we could do an organic chemistry unit, but we'll keep our fingers crossed that we'll still be able to do it. But just the way that the end of this year is kind of finishing up, we'll be lucky if we can do a good job on solutions. So this one, we'll learn, this is an organic compound. It's got carbon. Organic has nothing to do with being healthy or sometimes natural, all of these things. I don't know where this comes from. The word organic simply means that it's based on carbon. If you were to eat this or drink this, this would not be good for you at all, even though it's organic. Okay, you would be very sick. Okay, what is this? We'll learn what this is, but really it has to do with the kind of bonds that are here and the number of carbons. So there's 1, 2, 3, 4, 5 carbons here. These are all going to be single bonds in here. This is called pentane. Okay, so pentane, think about octane. Octane is kind of gasoline that you put in your car, or petrol that you put in your car. This is pentane, so it's a 5-carbon linear molecule. So, how do we know if they're miscible or not? Well, things will only mix if they are similar. Okay, so in some ways they need to be similar. So salt will dissolve in water because salt and water are in some way similar to each other, whereas oil and water will not mix together because they are not similar to each other. So we should be thinking, in what way are they similar? Well, what do we know about water? Let's start with this, because maybe you don't know anything about pentane, but you should know some things about water. What do you know about water? Well, first of all, we know that water, right, has this bent geometry to it, owing to those lone pairs of electrons. We also know that water is dipole-dipole forces, okay, because of the difference between the oxygen and the hydrogen. The bent geometry gives it it's a polar molecule, so it has these charge separations creating these dipoles. And because it's hydrogen and oxygen, it's a special kind of dipole-dipole called hydrogen bonding. It's a polar molecule. I'll put that, that's what that means, polar. Okay? What can we logically infer from pentane? Even if you probably haven't used pentane. Actually, we've got in the lab, we've got one with 6 carbons. I think we have hexane up in the lab, so we've got one with just 6 more than these. So what kind of bonding would exist here? So these are carbons and hydrogens. There isn't enough of a charge separation to make them dipole-dipole. There's no hydrogen bonding. There's no ion bonding. So here with our pentane, of course, this is going to have, all molecules have dispersion forces, but the polar nature is more prominent. Pentane will only have London dispersion forces in it. Pentane is not dipole-dipole. It is not polar. So pentane is going to act in a very similar way that oil acts when you mix it with water. Oil is based out of a lipid structure, biochemistry, but those are non-polar, and for very good reasons, because they form that layer in water. Why? Well, this is how your cells are made. This is how you can form layers inside your body where we can keep certain liquids separated from other liquids. This is very good, because if oil was miscible with water, we probably wouldn't have life as we know it here on Earth, because this is a very good thing. This makes up the chemistry of your cellular membrane, the reason why this works. So, are these two things miscible? No, they're not miscible. Why? Because water is a polar molecule and pentane is not polar. It only has dispersion forces. When we ask if things are miscible, the kind of mantra that you should always have is that like dissolves like. Okay? So water will dissolve something like salt because both of them are charged molecules. So they're able to dissolve. They're similar in some ways. What do you think we could dissolve pentane in? What would pentane be miscible in if we think about our mantra of like dissolves like? Ooh, and I hope somebody has the little light bulb that's going on saying, well, should be oil. Mr. Harrison, you said oil is nonpolar, the pentane's nonpolar, and yes, we would expect, and rightly so. So our pentane should be able to dissolve in some oil, some cooking oil, that kind of thing. Okay? I'm going to leave it there. Your questions are all posted up on Google Classroom. We'll do more of these examples on Wednesday. It's always a good chance for you to do some of these first so that you have some idea when I'm asking you questions on Wednesday about these things. And we'll do some more. We'll go through them. And then I think I may have one or two online labs about this we can do before we talk about types of solids. And then in the next couple weeks or so, we're going to start talking about solutions. Okay? Have a nice day. Play safe. Stay safe.